the stream. It has started. Come on. Calc2. And almost there. Homework list. Boom. All right, these were on paper. Wow, old school. Grab this page here. That's why I brought my glasses. 11.4. All right, comparison tests. How did you do? Could you figure out what to compare things to? Sort of. By the way, I don't know if you figured this one out, but when in doubt, it's almost always easier to just use the limit comparison test, because the direct comparison test, the one where you have to figure out which one's bigger and which one's smaller, that sometimes it's like, I don't know, is it bigger or smaller? And then if it's bigger, does that mean that it converges or diverges? And yeah, when you do the limit comparison test, it's like you've married the two sequences or series, and they go the same direction. Either they both diverge or they both converge, whichever way it is. So I find that the limit is almost always easier to deal with. Once in a while, the direct comparison is easier. So none of these, we don't have any problems? What do you think, Pearson?
13.
Okay, I know, you didn't have a problem with that one. You just wanted to make sure that I did at least one for the rest of the class. Thank you for that. So, number 13. Limit, I'm sorry, I'm not doing a limit yet. So number 13, we're doing the sum, trying, there it is. The sum where n equals 1 to infinity of 1 plus cosine of n over e to the n. So I just got done saying how the limit comparison is the easier one to use, except for in certain circumstances. Well, Pearson picked the one which is the certain circumstance. You could do a limit with this, but it's a little bit of a pain because you have to worry about the cosine and what happens to the cosine when n goes to infinity. Let's not worry about that. Let's actually just compare this to this series. Now, first you might say, where'd you get that? Well, here's where I got it. I know that 1 plus cosine of n, here, I'll just draw this, just a minute. Here is 1 plus cosine of n. That's 1 plus cosine, well, cosine of x. We'll go with x. And then this is 2. Okay, 2. And so you'll notice that if I've drawn that properly, 1 plus cosine of x is always less than 2. And it's always bigger than 0. So you're always in that zone between 0 and 2. So up here, this will be less than, sorry, I gotta get this right, less than that. And then this series is one that we're familiar with. It is a geometric series, and it converges. In fact, let me just rewrite it to make it look a little bit prettier. 2 times 1 over e to the n. 1 over e is between 1 and negative 1, and so this is a geometric converge. And so this one will converge. So that would be that direct comparison. But like I said, most of the time, you're going to want to go with limit. But in this one case, well, I don't know, there may be one other one on the homework. It turns out this is easier. What do you think, Tony? I sure can. Any other questions about 13 before we move on? So 13 was pretty easy once you saw, oh yeah, cosine of n. Yeah, sine of n does something similar. It'll go up and down. You can figure out where that's going to be. Okay, yeah, let's take a look at 21. All right, so 21 looks like this. 1 plus n over 2 plus n. Okay, so let me remind you of the sort of I don't want to say, it's sort of the shortcut way to figuring out what you're going to use for your comparison. So the shortcut is you pick the biggest thing in the numerator and the biggest thing in the denominator, and you make a fraction. So the biggest thing in the numerator is that in there, in is bigger than 1 most of the time. And so at least we're dealing with actually almost all the time here. So in will be bigger than 1, which means I'll just leave the radical there, but in is the bigger of the two things. If there were 3 things, I would pick the biggest of all of them. And then in the denominator, I've got in is bigger than 2. Well, as long as, for most of the time, you're dealing with this, which is a sum from 1 to infinity. So the vast, not even the majority, pretty much all the time, whatever in is, like 10 or 12 or 15, it will be bigger than 2. So put that on the bottom. So that's what I'm going to use for my comparison. And that's this, just to make it a little bit easier. So before we go on, Tony, you know about this particular series, don't you? If that was a series, does that converge or diverge? Did you say diverge?
Yes.
I thought you did. I wasn't sure, but yeah, this one diverges. And it's because it is a P series where P is 1/2 and 1/2 is less than 1, less than or equal to 1. So P series converges if P is bigger than 1 and diverges otherwise. So this one diverges. So now if we can link these two, then the other one will also diverge. So now we'll do my limit. So I do the limit as n approaches infinity of this fraction. Pick one of these to go on top, and the other one goes on the bottom. And then you just have to do some algebra. So just so you know what I just did, I took this fraction here, flipped it, and multiplied. So it's just some algebra. And then I'm going to simplify some things here. This is limit n approaches infinity. I know you all can do this, but let's just do it for fun here. N plus n squared. Okay, so now at this stage, we're doing a limit as n approaches infinity. You can use whatever trick you want to use. I'm going to use the trick that was taught to us by this textbook. So this textbook says you take whatever the biggest power is, which here is this n squared, but notice that it is under a radical, so it's actually n, and divide everything by n. I know you do it your way, and your way is quicker than my way. I know, it's going to take me forever, isn't it? It's all right. When that n gets put under this radical, it becomes n squared because the square root of n squared is n. And now I'm almost done. I know, tedium. 2 over n plus 1, square root of 1 over n plus 1. Okay, now I can finally do this limit. We know that the limit as n approaches infinity of 2 over n is 0. We know the limit as n approaches infinity of 1 over n is 0. And so all of this stuff ends up being 0 plus 1 over square root of 0 plus 1, which is 1. I know you probably just took this and skipped right on to this. Oh, not that one. That one. And that's totally fine. If you use whatever trick you learned, there are shortcuts to skip all of this stuff where you can just go right from here down to there. Fine. Doesn't bother me. But just, do whatever you learned. This is the correct way to do it. Tony, what do you think?
Does it matter which one you divide?
Yeah, you can do it the other way if you want. You mean flip this? Yeah.
Does it ever matter?
Nope. It will eventually, well, no, it does not matter in this context. So there will be a context in which it will matter, but that's down the road after Easter. So, but in this context, with this particular test, it doesn't matter at all. Do it whichever way is more convenient, whichever way is easier. Okay, so now these are linked because that is finite and it's non-zero. These are linked, so they will go to the same place. They are linked. So because this one diverges, this one will also diverge. I know a lot to do there. So just so you know, with the quiz, with the test, what I'm looking for is I want to see what is it that you're comparing this to. So what's the bare minimum? I know that's what's the most important thing is what is the bare minimum. Here is the bare minimum. This, that, explain why. And then something like this, this. So, I mean, I suppose that it might be helpful to have a little bit of intermediate work there, but the highlighted stuff is kind of like the bare minimum. You need to have a series that you're comparing this to. You need to have a limit, and then you have to have the limit. You know, as long as it's non-zero and not infinity, then you can say that they're linked. All right, what else we got? This it? Quiz. Okay, we'll do the quiz. All right, so we'll trade. Here you are. Maybe you can share these with some of your friends. And I don't know how many are here. Here, you can share those with your friends as well. There you go. And I give you a personal delivery. I'll come back for the homework. That. There's one. I have a whole bunch of extras for some reason. Thank you. Nice. Is this for me? This one? Sorry. Put this up on the screen. quicker than me. You all set? Is that right? All set? I'm not rushing you, am I? Okay, sure. Hopefully you're coming down the home stretch here with this. Write down some series you want to compare things to, and you can always just write converge or diverge and hope for the best. Nothing there. All set? All right. What do you think, Tony? Is it all right? All right. I am rushing you, but it's okay. And you felt rushed, but that's okay. I'm running. Almost there. Put down the thing you're going to compare to. Yeah, that'll be at least half of that. Yeah, there you go. That would be what you compare it to. Excellent. All right, nice job. Is it really less than? Greater than. All right, let's take a look at these. I did the limit comparison test for each one, but you might have chosen to do a direct comparison. So if you did that, yours probably was, well, I don't know, it just depends on the problem. In fact, yeah, the last one was probably easier to just do a direct comparison. So here's mine. So the first one, I compared it to 1 over n squared, which converges because this is a p-series with p equals 2, which is greater than 1. I did my limit with a lot of messy work here, and I got 1, which meant that the two series would go to the same place. Both converge, both diverge. So since this one converges, that one will converge. But number 2, similar, almost the same exact problem. I mean, the only difference, actually, yeah, what was I thinking? I should have just, yeah, this one is basically the same. Whoops. What just happened? What's going on? It's really little. Let's try this. Okay. Sorry. Okay, so it's almost exactly the same problem. So I didn't write down the whole P-series thing here. But yeah, so sorry about that. I should have had two separate, I don't know, different problem there. Okay, going on to 3. 3 was the one that was the most confusing, and so what I did there was I just took the biggest thing in the numerator, which is square root of n, and divided by the biggest thing in the denominator, n cubed, and I got 1 over into the 5 halves. I mean, you might have written it a little different than that, but whatever. It's still, that thing converges because this is a p-series with p equal to 5 halves, which is greater than 1. And then I did, yeah, this is going to be really ugly. So there's that, and I was rushing, but I did a bunch of algebra, and I got 1 for the limit, so that means they both converge. And then the final one, you're comparing this to just 1 over n, which is 1 over the square root of n squared. This one I realized, yeah, just now, it would have been a lot easier just to do a direct comparison, because you could just say that this is actually bigger than what you get if you get rid of the -1 there. Because if you make the, wait, let me make sure, is this right? If you make the denominator bigger, get rid of the -1, what you end up with is smaller. So that's actually smaller, and we know that diverges. It's got a name. It's the harmonic series. So that diverges, which means that this one will. But I actually did the limit as well, and there's my limit, whatever. Why did it take so long? I don't know. Whew. Okay, we're done? No, we're not done. We're done with the quiz. So questions about the quiz? What do you think?
Go back to 2.
I can go back to 2. 2 and 1 were basically the same problem.
Why did it go positive?
What did go positive?
Go to the bottom.
Oh, because that's just I messed up here. There, is that better?
You would still a positive.
What are you talking? Oh, here. Is that better?
No, it's negative.
Yeah. No, it's still positive 1. Because you're doing the limit as n approaches infinity of this, so the, oops, now that went away. So whenever you have the trick that you can use is you take the highest thing in the numerator, highest power in the denominator, and just everything else doesn't matter. So n squared over n squared is 1. So positive 1. Regardless, if you got a finite number, even if your finite number was the wrong limit, at least your reasoning was correct that they both will either converge or both diverge. So anyway, but that's the correct limit there. Anything else? All right, we have some reminders. So reminders about the series that converge. So these are the ones that you should have in your brain that you should that are stuck there. So we have geometric. The geometric series. This is this series where, let's see, we'll go n equals 0 to infinity of let's just call this a times r to the n. So I can put an example down, but we're used to this, I hope, by this point. And this thing will converge as long as r is between -1 and +1. And we know what it converges to. It converges to a over 1 minus r. Now I know that this formula only works if you start at 0, and so because of that, I like to think of this way. It's the first term over 1 minus r. Just so that if you start at some other number, for example, let me just do a quick example, and these are all reminders, hopefully. Let's say we do n equals 3 to infinity of 7 times 1/3 to the n. There. So if we use this, then the common ratio is 1/3, and that is between 0 or -1 and +1. So that checks out. And then this thing will add up. The sum will actually be the first term, and the first term in this case is what you get when you plug 3 into that. That would be the first term of this series. It's, what's that? 1/3 to the third is 1 over 27. So you'd have 7 over 27 all over 1 minus r. So notice I'm using this. And what does that work out to? 2/3 on the bottom, flip this baby over, and you get 7/18. The final answer. So anyway, just wanted to do a quick reminder of that the geometric series, it converges when r is between -1 and 1, diverges otherwise. Another quick reminder, and then we'll get on to remainders. So another reminder is this, that a p series, and I know we've gone over this, we just did it, but I want to make sure we get this because it's on the exam. So n goes from 1 to infinity of 1 over n to the p. This converges when p is greater than 1, and it diverges when p is less than or equal to 1. So you have that rule. We used it a bunch just a minute ago, so hopefully we don't need an example of that rule. Whew. Okay, so we've got that. Next thing that we kind of glossed over, it kind of popped up in the homework, and so I need to make sure that we do it for real, is remainders. What is a remainder? A remainder is what remains after you add up a bunch of terms of a particular series. So let's say that we were doing this series. Let's see, pick one that actually converges. Give me a sec here. How about 1 over x times the natural log of x? And we're going to, x, we need to use n, sorry. N times the natural log of n, where n goes from 2 to infinity. All right, first things first. This is a quick review, I guess, another reminder, and that is we have to check to see whether this converges or diverges. And the way we're going to do this one is we're going to use the integral test, also on your test, or your exam. Integral test. Let's see. Okay, so the integral test, what we do is we do the integral from 2 to infinity of 1 over x ln of x. And you check to see, is that finite or is it infinite? The reason why we can use the integral test is this, that 1 over n ln of n, okay, how about this? 1 over n ln of n is always bigger than 0. That's the first thing you have to check. The second thing you have to check is this. Is that 1 over x ln of x is decreasing. I'm not going to actually do this, but the way you would do it is you would do the derivative and check to see that the derivative was always negative. But anyway, this thing is always decreasing. Some functions, it's obvious. This one is pretty obvious, but it may not be super obvious to you. Something like this, 1 over x cubed, is pretty obvious because you know what the graph of 1 over x cubed looks like. It looks something like that. So this is always decreasing. Yeah. Okay, so getting back to this, let's actually do this integral. I know it's scary. Yeah, what do you think?
What's the point of doing the integral test if you can do comparison?
Okay, yeah. So there may be some series for which the comparisons are inconvenient, like this one. What are we going to compare this to? X times natural log of x? I mean, that x times natural log of x is smaller than 1 over x, and it's bigger than 1 over x squared. So figuring out what you compare this to may be a little tricky. So that's a good reason to use this. Another reason is where we're going with this, which is the remainders. So we'll get to the remainders in a minute. I just need to remind you of the integral test before we do the remainders. Anything else? Yeah, other complaints? I'm happy to try to answer those. Yeah, you're right though. And to be honest, moving forward after Easter, the integral test is kind of like a test of last resort, because who wants to do an integral? I don't want to. There are other tests that are going to be more efficient. And actually after Easter, we will learn about a test that will make this almost obsolete, but not quite. It still is useful every now and then, especially for the remainder thing. The remainder thing, it's very useful. That's why I'm reminding you. We're reminding about remainder. Okay, next. So let's actually do this. So here you may feel like this is too much work, but let me actually do it. U is equal to the natural log of x. Du is equal to 1 over x dx. Hopefully you can see right here that this is going to be the integral of 1 over natural log of x times 1 over x dx. So you see where everything came from and where it's going? Darn. Sorry. I thought that this would converge. This is not going to converge. Oh well. I'll have to pick another one. I was hoping I'd get something interesting so that Tony would be happy that it was something that we couldn't just do using the comparison tests. Well, anyway, let's go ahead and do this and see that this diverges. Okay, so this thing, when I do u, change to u, this becomes du, so it's 1 over u times du, and that's going to be the natural log of u. And so now I'm going to change back to my original x. That's going to be the natural log of the natural log of x, evaluated from 2 to infinity, and that diverges. Sad. Well, it still is a reminder. It's a reminder that when the integral diverges of an integral test, then the series diverges. So this thing will diverge. Okay, well, let's talk about remainders. And I won't bother with something that I'm trying to be clever with. So this one, you already know that this converges. So we'll talk about remainders though. So n goes from 1 to infinity of 1 over n squared. We already know this converges, right? This is a p-series, where p is equal to 2, which is greater than 1, so this converges. Done. Well, we're not quite done. I want to know what it converges to. And this is a question that was that mathematicians worked on for, I think, about 100 years, until finally Leonard Euler figured it out back in the 1870s, I want to say, figured out what this actually converges to. But we don't know what it converges, well, I know, but let's say that you don't know, but you want to know approximately what it converges to. So what you could do is you could do this. 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. What just happened? Did something happen? I saw something blink. That's working. This is working. Okay, it's all working? Sorry. How far do you want to go? Tell me when to stop. Stop? I think I heard someone say stop. Okay, I'm going to pretend because I don't want to go any further. Okay, so we've got 1 plus 0.5 plus 0.1111111 plus 4 squared, 16. That's, okay, I'm going to have to use my calculator now. And I know that that's plus 0.04. I know what 1 over 25 is. Let's see, 1 over 16, 625. 0.625. 1 over 36, 0.27777, etc. And then 1 over 49, which is 0.02. I'm going to round. It's actually 0.02 something. We're going to leave it at 0.02 because, oh, I do have space. Okay, let me add these up. Give me a sec. So plus, let's see, 1.5 and 1.9, almost there, 0.625 plus 0.0625, 0.04. I'll type in 1 over 49 just to make everyone happy. Okay, so I've got 1.761797. The question is, how close is this to the truth? Well, we can actually get an estimate for how close we are to the truth because we have the integral test. Let me just show you pictorially what's going on with the integral test. So you have this series. Basically, it's a sequence of numbers, and I'm representing that sequence with a bunch of bars. And then you have this function that matches this function up here. And I'm going to stop after how many? 1, 2, 3, 4, 5, 6, 7. I guess I could have just looked at the last box. 1, 2, 3, 4, 5, 6, 7. So the stuff that I'm leaving off are all of the little rectangles. The error is all the rest of the rectangles. Well, it turns out that all the rest of the rectangles, which I don't want to have to draw in here, so we're stopping here. Anyway, all of those rectangles are smaller than the area there. So to estimate the error, how much error is there? Well, the error is going to be smaller than or equal to all of the rest of the rectangles, which is the integral from wherever we stopped. In this case, we stopped at 7. It's the integral from 7 to infinity of this thing. Now, let me bear with me for a sec here. We're going to actually do this, but I'm going to move this over because I need to write one more thing here. Okay, so that error is going to be less than or equal to this. So let's see, how close can we expect to be? So this is going to be 1 over x evaluated from 7 to infinity, which is equal to 1/7. Well, that's not very encouraging. Did I do that right? I did do that right. So I can only expect to be within 1/7 of the true answer. However, I can also say this, that my error, for geometric reasons that I can't really draw because it's kind of run out of room here, but this error will be bigger than this. So notice that the difference here is that the error is going to be less than 1/7. That's the number that we stopped at. Or sorry, 7 to infinity. But it's going to be bigger than the next one from 8 to infinity. So let's go ahead and compute that. So this is going to be negative 1 over x evaluated from 8 to infinity. And I'm not going to bother with the details here, but that's going to be 1 over 8. So I'm between 1/7 and 1/8 of the truth. So let's go back here and see what the actual truth is. So like I said, Leonard Euler figured out what the truth was. The actual answer is pi squared over 6. So we can do this on our calculators. So pi squared divided by 6 is 1.644. So let's see. So the truth is 1.6449. And you'll notice that the difference between these two is actually, what, 0.12? And if you do 1/7, you actually get 0.14. So we're for sure we're within 1/7 of the truth. And so that's what this remainder does for you, is it tells you how close you can expect to be with, of the truth if you just add a certain number. So that's another reason why we like the integral test. So remainders for the integral test is just the rest of the series. All right, so alterations. Okay, honestly, I don't have any alterations. I just thought that it would be funny to do that with the one letter that's different. Reminders, remainders, alterations, alternations. Okay, so we need to do the alternating series thing here. Okay, what's an alternating series? An alternating series is a series where you have both positive and negative terms. So far, series that we've been dealing with have just positive terms. Alternating series are series that alternate, positive, negative, positive, negative. Technically, we have had some of these. For example, this one, negative 1/2 to the n power. That is an alternating series. Let me write down the terms. Sorry, I just wrote the wrong number, or wrong symbol. Let's try again. So 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16 minus etc., etc. So that's an alternating series. It alternates positive, negative, positive, negative. This particular series is geometric, so I know the sum. This one converges because it is geometric. But in general, not all alternating series are series that we are familiar with. For example, let me make a new series that alternates and see if you can think if it's going to converge or diverge. So how about that one? So let me write down the first few terms of this series. This series starts off with negative 1/1, and then we add to that 1/radical 2 minus 1/radical 3 plus 1/radical 4 minus 1/radical 5, etc., etc. So that one is a little bit harder to tell. Does that converge? Does it diverge? So intuitively, you might have an answer, but let's see if your intuition is right. Maybe you could take a guess. Does that converge or does it diverge? Now, the trick with alternating series is that if the series looks like this, and I'll explain what I mean by looks like this in just a sec, but if it looks like this, then for sure it converges. Now, you might say, well, what does this look like? It doesn't look like a convergent series. You're familiar with this as a p-series. If it wasn't for the plus minus, you would say that diverges. But the plus and minus, what that does for you is it does this. Let me write down the partial sums. We have negative 1. And then I add to this, now I regret choosing this particular series. So let's see, 1/2. And I got, so this is going to be negative 0.293. Good enough. So that represents the sum of these. Now I'm going to add to this, to add that in. So plus negative 1 divided by the square root of 3. Uh-oh. Sorry, took a minute there. And that's going to give me this, negative 0.870. And then I'll add to that, this one I can do in my head, that's 0.25. No, it's 0.5. 1/radical 4, that's 1/2, 0.5. So then the next number will be negative 0.37. And so on. If we were to chop this off here, we would get something a little bit, well, more negative than this. But you'll notice that the series, as you chop it up, if you do these partial sums, they don't get big like they would if you were doing 1/√n without the negative. And that's because you're subtracting a term, then adding a term, then subtracting. So we're always adding and subtracting. And eventually this is going to settle down. So what's the rule? The rule is this. If you have an alternating series, and one thing you have to check is that, okay, let's see. Oh, here's a picture of at least one alternating series, and that is, so these are the terms, but here is the actual sum. Notice that it goes up and down always, but it's always getting closer to a particular number. But anyway, here's the, okay, another one, lovely. There's the rule. We'll go back to those pictures. They're interesting, but let's look at the rule first. The alternating series test says that if you have an alternating series, and so this is the general form for an alternating series. You have negative 1 to some power. It's n minus 1. This is the book, so sorry, I'm stuck with whatever they have. I would have put in there because it's easier to work with. But anyway, negative 1 to the n minus 1 times some b sub n. The b sub n is some formula, let's say. Anyway, this is what you're going to end up with. B1 minus B2 plus B3 minus B4 and so on. You're alternating back and forth between positive and negative, hence the name alternating. Next, you want to make sure two things happen. First of all, the b's are getting smaller. As long as the b's get smaller, and secondly, the limit of the b's is 0, then for sure the series will converge. Doesn't matter, that's all you got to check is those two things. So let's go and take a look at one of these. Does this converge or diverge? So first thing to check, let me write down the b sub n. B sub n is this without the negative 1. So basically you take whatever formula you have there and write it without the negative 1 part. So get rid of the alternating thing. So first things first. Oops. Well, okay, apparently I have it. Let me erase these things. There. Okay, so b sub n is 1 over n. So the first thing you need to check is, do the numbers get smaller? Is 1/3 smaller than 1/2? Is 1/4 smaller than 1/3? Will that always be the case? And so to make sure it's always the case, here's how I do this, is I ask myself, is 1 over n plus 1 always going to be less than 1 over n? And the answer is yes, it will be. That is true. Sometimes you have to do a little bit more math or algebra to show that that's the case, but in this case, I think we can all see that this number, whatever n is, doesn't matter, 1 over n plus 1 will definitely be less than 1 over n, because the denominator is bigger. Okay, so that's taken care of. The second thing we have to take care of is check the limit. The limit as n approaches infinity of that thing. And so the limit as n approaches infinity of 1 over n is 0. And so I've checked that. And because both of those are true, I know that this series will converge. So notice for all of these alternating series, you're just checking these two things. And based on your answers, you're going to conclude either that you converge or you don't converge. Diverge. Okay. Yeah, if these are not true, okay. If this is not true, then for sure you diverge, the second part. The first one, yeah, that one's trickier to deal with. So we'll not worry about that for now. All right, so try this one. Does this thing converge or diverge? Now let me help you out. In fact, why don't you help you out? Here's the things you're going to do. You're going to do this. What is b sub n? Remember, b sub n is just whatever doesn't involve the negative. And then secondly, is b sub n plus 1 less than b sub n? And then finally, what is the limit as n approaches infinity of b sub n? So take a minute, see if you can work these out. And I'm going to interrupt you in just a sec because I want to make sure that we're all on the same page with b sub n. Here we are. All right, Owen, what is your b sub n? So as a hint, just read everything that's up here except for the negative 1 to the end. There you are. Yeah, 3n over 4n minus 1. That's all you got. So start with that, and now ask the question, or answer the question, is bn plus 1 less than bn? And then finally, and if you want to, you can skip to the last part if you're confused about that second question. So yeah, so notice there's 3 things you have to do. 1, 2, and 3. So you can skip to the third one. The third one's pretty easy. We only have 5 minutes. So, yeah. All right, so I mentioned that you could have done 3 first and then 2, but I don't want to give away 3 before we do 2. Sorry. So let's do 2, suffer through it. So Pearson, what do you think of number 2? Is b sub n plus 1 always going to be less than b sub n?
Yes.
Yes, it is true. How do you know? It just looks that way, yeah. Yeah. So yeah, you can do 2 things. I'll do it the wrong, well, I shouldn't say the wrong way. I'll do it the not quite right way, and then I'll do it the right way. So the not quite right way would be this. Just write down the various terms. There's 3, that's for n equals 1. When n equals 2, I get 6 over 7. With n equals 3, I get 9 over 5, n equals 3. 9 over 11, n equals 4, 12 over 15, and so on. And you can just sort of visually check, go as far as you need to make sure that you're seeing, oh yeah, they're getting smaller. Okay, so what if you didn't know for sure? Then you could do this to prove it. 3n plus 1 over 4n plus 1 minus 1. Is that less than, question mark, 3n over 4n minus 1. And so you can multiply both sides by the denominators. So 3n plus 1, 4n minus 1. Is that less than 3n times 4n plus 1 minus 1? And so a couple of things to note here is, let's see, oh, actually, yeah, is it true? I have to do a little bit more algebra here. 12n. Yeah, I don't know if we have time to do all this algebra. Yeah, let's stick with the cheater method for now, especially since the homework's on WebAssign, so they don't know. Finally, the limit. Let's do the limit, and then we'll be done. This just is going to take some time here. So that one's a little bit more complicated than I thought it would be. But Sarah, do you know the limit as n approaches infinity of this thing? It is 3/4. 3/4. That is not 0. The only time you converge is if that equals 0. This one does not converge. This one actually diverges. So anyway, do your best. The homework, quick preview. Yeah, test 3. We'll talk about this tomorrow. Basically, tomorrow is just everything except for these 4 items that are below my hand. So it's homework, quiz, test 3 preview. So you'll have plenty of time. Be sure you look, though, online at the practice test and do the homework, which is on